Hi, this is the project about pipeline NIOSII implementation as hardware. I have implemented the RISC processor along with NIOSII instruction set architecture in this project. To begin with, I would like to give an overview of the NIOSII processor. It has 32-bit instruction set architecture. It is basically designed for Altera FPGA, which has a RISC architecture, and RISC stands for Reduced Instruction Set Computing. And NIOSII has three versions called NIOSII-F, which is fast, NIOSII standard, and the third is NIOSII economical. We will be implementing our project on the economical version. So let me introduce you to the NIOSII instruction set architecture. There are basically three types of instructions in NIOSII, which are I type, R, and J type. I stands for immediate data assignment, R stands for register to register transfer, and J for jump. The I type register is shown over here, which is an example of for add immediate instruction. This is the add immediate instruction, which is 32-bit long. Let me remind you that each and every instruction in NIOSII is 32-bit instruction. So accordingly, this will be a 32-bit instruction, and the operation performed over here is basically this. RB is the destination register, RA is the source register, and immediate value is being added to RA and then assigned and stored in RB. The first 6 bits over here is for the opcode of the add I instruction, which is 0x3a. The next 16 bits stands for the immediate value that need to be assigned, that need to be added. And over here, the last digits are for the registers. Then there is R type. In R type registers, other R type instructions, we will demonstrate add. In this, 0x3 is the opcode. Then other 16 bits are for opcode extension, which in case of add will be 0x31, and all other bits will be assigned 0. And there are three registers, register A, B, and C. Register A and B are the registers whose values will be added together and then stored in register C. So because the values are being computed from the registers and then stored into register, this instruction is called an R type instruction. This register the register. Then we will see the J type register, which is also a name for jump instructions. We will see an example for call subroutine. In J type instruction, the first 6 bits are opcodes, of course, when other 26 bits are used for immediate value, which forms the address for the destination where the jump should point the program counter to. So over here, if I call subroutine, the program counter will be incremented and then it will be stored in this place. Now we will see the registers in NIOSII. There are 32 general purpose registers in NIOSII. Each and every register has a different function and they are very useful for computation. As shown over here, the register R0 and R1 are of importance. Moreover, the registers R27, R28 and R31 are very important for jump and stack computations. We'll be using R27, 28 and 31 a lot in our programs over here. So now this is a pipeline processor, which is a RISC implementation of NIOSII. It has basically 5 stages. First stage is instruction fetch. Second is instruction decode. Third is execute. Fourth is memory, and fifth is write back. We will study each and every stages in detail in the slides coming next. With its values, and the instruction will be fetched from this instruction memory, and then it will be stored in the register over here, which is called instruction fetch instruction decode register. In second stage, this register will pass the values to the instruction decode stage. Over here, the instruction registers are selected from the register file and then stored into the instruction decode execute registers. In third stage, the values that these registers pass to the intermediate registers is getting supplied to the ALU through this MUX, and then this MUX will be computing this ALU will be performing the operation of add or subtraction or whatever, and give this output to this register. Over here the instruction is add, so basically it will be supplied, the addition will be supplied to this register, and in cycle 4 the add will be taken out over here, and it will be put in the data memory, and then it will be going to the MUX, and this is the write back stage. In this write back stage, we need to write back the output of ALU to the register 3 that is in this register file. So in this stage, the path is like this. It will be directly writing to this register over here, and we need to remember that each and every cycle is performing different operations at times, so we are actually increasing the latency of our design. However, we are improving the throughput each and every cycle. So you can see that taking is the example of add I waveform. Over here the opcode is 04, which is for add. The two registers are added over here. The immediate value is added to R2, and the result we get over here is 24. So my conclusion over here is that I found out that the total instructions for factorial is 31, number of clocks required is 145, and the CPI, that is the total number of clock cycles per number of instructions, I'm getting it for factorial is 4.678, which is not that bad, and for dot product I'm getting 4.55 in similar fashion. So what is the future work in this project? In this project, I have not yet implemented the whole NIOSII processor on a FPGA board. I have just simulated it. However, it can be implemented on FPGA board and can be checked for performance in real time. RAMs can be used for instruction memory, data memory, and register file for faster access. And latency can be decreased by using forwarding unit in order to compensate for stall cycles, and one can also use Tomasello algorithm for dynamic hardware scheduling that may also increase the latency. So this work I will be doing in future again on this project, and